Good morning, everyone. Before we get started, so they finally released the Exam 3 scores. Hopefully you had a chance to look at your score. The overall 1210 average was about a 75% in that range. So you can get a sense kind of how you're doing relative to the class. Our grade scale is kind of set in the syllabus. So if you were wondering about grades, just check the syllabus. It's like 92.5% in ups and A, 88.5% in ups and A minus. I think 84.5 B plus, et cetera. That's kind of our curve that's built into the class. So sometimes I get asked, do we curve? Any curving was already considered onto that grade scale, and it is generally more generous than the OSU grade scale. As you go slightly down in grade, it's a little bit more generous on that grade scale. We still have half of the exam points left to go, so midterm 4 is worth 10%, the finals worth 20. So we have a lot of points still left to earn, so I don't think anybody's locked into any grade at this moment in the class. And then also, if you look at the lab, the homework, the recitation, lecture attendance, we're running probably about a 37 to 38 out of 40% average on those points in the class. So in other words, you guys are doing really, really good on all of those points. That's 40% of the class. So if you're doing really good on all those areas of the course, you're padding that on top of your exam score. So if you're hoping to get to that 92.5% exam score average, as long as you're getting a lot of the other points, you can have an exam average that's lower than a 92.5 and still end up in the A solid range. Same thing with the A minus range and all the other ranges. You can generally average at a score slightly lower than that grade range with high scores on the lab, homework, recitation, and lecture scores. As we finish the course up, try to make sure that if you have missed a couple recitations, go to the last couple recitations. That'll really help your grade. Do the last few homework sets. You can still earn late credit for past homework sets. So if you've missed some post-lectures, you can still get up to half of the points for those assignments. If you haven't noticed that a lot of the questions are in the readings, doing the readings will help you on the post-lectures. But I think most of you guys are averaging very high on those assignments. I don't think there's a whole lot of you guys looking to earn more points in lab or recitation in those areas. But if you have been losing points, definitely find a way to not lose those points down the stretch. That'll help your grade as we finish up the class. And then lastly, I think for exams, doing practice problems with the book closed is really helpful. So doing daily quizzes as often as you can, focusing on taking practice exams like a real exam, getting yourself into test-taking mode. I think it's easy to learn how to do a problem with the book open. The key is being able to do the problem, obviously, book closed. I think we just have to have a lot of practice in that test environment or test-like taking environment in order to have success on exams. Chapters 8 and 9 are going to be very intensive on Lewis structures. So if you don't learn how to do a Lewis structure, something's probably gone wrong. So we're going to keep coming back to these Lewis structure rules throughout the next chapter 2. When we get into chapter 9, we'll also still be sketching a lot of Lewis structures. So we're looking at these rules here today. Again, we're going to push forth into some more molecules. So we're summing up our valence electron count. So hopefully we're just picturing our valence count is just alkali group, like the lithium group is 1, the beryllium group is 2, boron group is 3, carbon group is 4, nitrogen 5. So nothing too crazy in terms of coming up with our valence electron counts. Identifying the essential atom is usually just given to us almost always by either the first atom, like phosphorus will be the central atom in PO4 3-. Hydrogen can't be the central atom in H2CO3, so it's going to be the carbon. We usually will give you the central atom kind of in linear sequence. Hydrogen sometimes can start the formula like H2O. Hydrogen's not going to be a central atom. Hydrogen can't form 2 bonds, so it's never going to be your central atom since it only can form 1 bond. So it's usually not too hard to identify the central atom. We complete the non-central atom octet. That's the key, is that we don't complete the central atoms octet with electron pairs, but we try to do so on the non-central first. And then if there's any electrons left over, they can go on to the central atom. And then if we need to reduce the number of electrons we used, or if we want to consider multiple bonds, we start to look at the relative charges. So that's the rule that we're going to try to get into here. With a couple examples, is when do we use multiple bonds and when does this issue come up? So let's look at PO4 3-. So phosphorus should have 5 valence electrons. So I take 5 and then 4 times 6 for O. And then the charge gives me a +3 because I have to add 3 electrons to get to that -3 charge. If I don't add these 3 electrons, then I would have a Lewis structure for just PO4 without that indicated charge. So I have to add 3 for the 3- charge. And so that gives me 32 total electrons that I have to distribute within the Lewis structure. So the Lewis structure that's valid for PO43- should have 32 electrons, and not 30, not 34, but precisely 32 electrons. And so then I start with my central phosphorus. I attach the non-centrals to the phosphorus atom. I come back to the idea that this isn't the shape of the molecule, or it's not necessarily going to be a molecule that looks flat. So we're going to talk about 3D shape later. So don't necessarily think that when you're sketching a Lewis structure, you're trying to think geometrically, where would these atoms be? You're just trying to see, am I going to use double bonds, single bonds? So we start with single first, complete the non-central atoms octets with lone pairs. And so that just is to give each central atom 8 total electrons. So we need 3 pairs of dots around the atom. And so each O looks identical, and each O has 8 electrons. There's 4 of them. So that's all of my 32 electrons that I had to distribute for this molecule. So I subtract my 32 electrons just to make sure I see I have none left over. So no lone pair onto the phosphorus atom. And then the next issue is, well, what are the formal charges? Formal charge is looking at the atom if we break the bonding pair electrons in half. So if I break one of these bonds in half, then I would have oxygen with now 7 electrons closest to it. And so what would that formal charge be? Well, oxygen should have 6 electrons for a neutral charge, and now it has 7 electrons closest to it, so that gives it a charge of -1. So all these O's are negatively charged with a -1 charge. And that just means, assuming the bonding pairs are equally shared, what is the charge for an atom that just simply looks like this? So that's oxygen that's picked up 1 electron. That's how we get to that this is just O-, or O-1. So if oxygen had 6 electrons, it would be neutral. So adding electrons goes negative, taking electrons away would go positive. Now what about phosphorus? How many electrons does phosphorus have closest to it? So again, just picture breaking the bonding pair electrons in half. And then the phosphorus atoms in this structure look like this. And so what's the net charge of that phosphorus atom if it looked like this? So if we had phosphorus with just 4 valence electrons, should have 5 valence electrons for a neutral charge, only has 4, so that's a +1 formal charge. So we have a positive formal charge for phosphorus here, +1, -1 for each of the O's. We mentioned before that the sum of the formal charges across the whole molecule should sum up to the charge on the molecular ion. So I have -1 times the 4 O's, +1 for the phosphorus charge. That gives me the overall charge of -3, which is what I should have. So you can do a double check that your formal charges should all sum up to the overall charge on the ion. If it's a neutral molecule, they should all sum up to neutral, sum up to 0. Now, the next question would be, well, should I consider a multiple bond? If there's, can we expand beyond an octet too? So like if I look at phosphorus and say it has a positive charge, and I can reduce that charge making a double bond. So if I go to phosphorus and I make a double bond between one of the O's, so let's say I take an electron pair here, and I move this electron pair to make a double bond between phosphorus and O, then I'll have something that looks like P double bond O, and then oxygen's here, remaining exactly as they were before. So notice that the O with the double bonds lost the lone pair of electrons because they've moved in to make the double bond between the phosphorus and the oxygen. Now, the benefit here would appear to be that we've reduced the magnitudes of charge. Now, the phosphorus has 5 electrons closest to it. So in terms of phosphorus, we have 1, 2, 3, 4, 5 electrons closest to it. So it's now a 5 - 5 for neutral. And the oxygen with the double bond is now 6 - 6 for neutral. And then my other oxygens are -1 as they were before. So I have like 3 negatives and a 0, still adds up to -3. So what's wrong with this? So reducing magnitudes of formal charge may allow octets to expand if it leads to lower magnitudes of formal charge, and the central atom has to be in the 3rd row or greater in order for this to be considered. So if this were like a nitrogen atom, we'll do an example with nitrogen in a couple slides, and see that nitrogen 2nd row atoms can never expand their octets. It actually is kind of almost the case too that third rows really can't either, but within some Lewis structures, you'll see this Lewis structure considered, and sometimes it's called the Lewis structure that satisfies the so-called formal charge rule, minimizing magnitudes of formal charge through using multiple bonds. But the key is you have to be third row or higher to expand an octet, and we'll see some Lewis structures, we'll see quite a few Lewis structures actually that expand octets. We saw one last time, SF4. If you recall the notes at the end of class on class on Monday, SF4 was an atom that had sulfur with 10 electrons around it. So we will see some Lewis structures that expand octets, but it will always be third row or higher when we see that, and not second row or lower. Now, which of those two Lewis structures is better? Now, that's a question that's tricky. If you look at computational modeling, the Lewis structure that maintains the octet rule is actually the better Lewis structure. So it seems as if this structure here better matches reality. It also turns out that all of the PO bonds are the same length in this ion. Like double bonds are usually shorter, single are usually longer. It turns out phosphate doesn't have one shorter bond and 3 longer bonds. There's also a topic of resonance that we'll soon talk about, where there can be a model where a double bond can resonate through a structure. But the PO bonds are all the same length, and it seems as if computational modeling suggests that we don't usually expand octets if we can just maintain the octet rule being satisfied. So and we'll see some examples of this too, where once you get to a Lewis structure where you have the octet rule satisfied and you're thinking about expanding the octet to reduce formal charges, you theoretically can do that to satisfy the formal charge rule, or you can maintain satisfaction or agreement with the octet rule. So you'll see some examples of old exam questions that'll say, show me the Lewis structure for a phosphate that satisfies the octet rule. Well, that's this one. Show me the Lewis structure that satisfies or minimizes magnitudes of formal charge, and that would be this Lewis structure. And then you'll see some questions that might say, well, what's the best Lewis structure? And then that would also be this one here. Our exams usually just ask for the octet rule satisfied Lewis structure, or the one that minimizes magnitudes of formal charge Lewis structure. It's very clear in the Lewis structure that we're looking for. On exams, you're not sketching Lewis structures. You're choosing maybe from pictures on an exam that are provided to you, so you never really have to sketch. A lot of times, if you're given options which Lewis structure is best for something like phosphate, we'll give you choices that will have the wrong electron counts, that will have multiple double bonds, that just, some will add up to 30 electrons, some 34. So sometimes it's just checking the electron count. But usually most Lewis structure questions on the test, think about going through these rules here. Think about trying to come up with what you think the Lewis structure should look like, and then find the best structure that matches that choice from the given options. Let's move on to H2CO in terms of the Lewis structure for, this is formaldehyde, is what that's the formula of. You could write it H2CO. Sometimes you see the formula written this way here too. So you'll see a couple different ways of sketching the formula. These are both representing formaldehyde. And again, hydrogens can't bridge, so hopefully we're picturing this as a central carbon, has an oxygen attached, and then has the 2 hydrogens attached here. If the hydrogens were attached to the O, we would have written the formula in a different way. Like when we write like methanol, if you recall, like when we have a hydrogen attached to the oxygen, we write it like specifically after the O in the formula. So, hopefully you can see by the way we write formulas, we're trying to give you the order of the connection to the central atom. So 2 hydrogens and an oxygen attached to a carbon. I could have started, or maybe I should have started with the valence count, but let me just go ahead and fill oxygen's octet in with lone pairs first, since that's one of our basic Lewis structure rules, is to start there. And so then for H2CO, we'd have 1 valence electron for each of the hydrogens. We'd have 4 for carbon. This is just based on the periodic table. So I'm just looking at the atoms placement on the periodic table to come up with these counts here. And that gives me a total of 12. So I should have 12 valence electrons shown for formaldehyde. And so far in my Lewis structure, I have 2, 4, 6, 8, 10, 12. So I've used all of my 12 electrons that I have available. So no lone pair for carbon. So remember, your rule is complete the non-central atoms octets. Hydrogen's good with no extra electrons, just a single bond for hydrogen's good. And then for oxygen, lone pairs around. And then I don't put any lone pairs on the carbon. So I don't look at carbon and say, okay, it's deficient right now of an octet. It only has 6 electrons. Do I put electron pairs here? No, because I don't have electrons available. That would be too many electrons. So now the next question is, well, do I make a multiple bond in this case? Well, this case here I think is going to be pretty easy to think. I have two good things going to make a double bond. I have carbon deficient of an octet. It would like to have, if it could, 8 electrons surrounding it. It only has 6. Remember, to think about the octet, think about the whole, all of the bonding pairs that surround an atom, all the lone pairs that surround an atom. And right now we only have 6, not 8 around carbon. And then its formal charge, we should have 4 electrons around carbon for a neutral charge. We only have 3 right now. So that's a +1 formal charge. And then oxygen should have 6, and it has 7, so this is a -1 formal charge. Now I write those dots as dots, but the dots are electrons. Electrons are negatively charged, and so these dots, you can imagine, these are really negatively charged particles. Let me take one of the pairs and just write them more discreetly as like negative particles. Just that you're picturing those dots are really negative, have negative charge. And so you can imagine these negative particles, they can be pulled in by that positive charge, especially if there's room for those electrons to go into the valence shell of that atom. So you can think, does the central atom have a charge? Does it have a pull for the negative electrons to be pulled in to make a double bond? And we do here. So we have the perfect situation to end up with a double bond here, and we've lost the lone pair on oxygen as a result. And then we have our 2 hydrogens here onto the carbon atom. And so now all of our formal charges are 0. And so the formal charge of hydrogen should have 1, and it has 1. So 0 for the 2 hydrogens. Carbon should have 4, 1, 2, 3, 4. So it's neutral as well. And oxygen should have 6, and it has 6. So it would be neutral as well. Usually in a Lewis structure, we indicate the non-zero formal charges. So I usually won't always write the zeros in. In fact, rarely will you see the neutral charges written on a Lewis structure, but we usually want to indicate the non-zero formal charges. So these are all 0. This is good. So this makes this here the best Lewis structure for formaldehyde. It actually makes this one not even a valid Lewis structure at all. So once we get to the point where we're not even satisfying the octet rule, and we can see that we can minimize the formal charges, so that means reduce the magnitudes of the formal charge from +1, -1 down to 0, 0. Through making the double bond, and then we're also leading towards the octet rule being satisfied, then we end at that structure and call this one here for formaldehyde the best Lewis structure. So that would be the best Lewis structure. Sometimes we use the word dominant. I don't know, I don't like that word too much, but the textbook uses it. So the dominant Lewis structure for formaldehyde would look like the one we've boxed in here. Okay, so let's go. Let me add a slide in your notes. The next slide had the examples we went through last time. I just wanted to call your attention back to SF4 that we worked on last time, where we had 6 + 4 × 7 for the fluorines, 34 total electrons. If you recall, we ended up with this Lewis structure here, where we had 5 fluorines, lone pairs around each. Sometimes I get asked if you can write the lone pairs this way. I don't like to sketch the lone pairs as lines. It doesn't make too much of a difference though, but I usually prefer to put the 2 electrons just so I can always think that they're pairs of electrons being exchanged. And then that was 32 of my electrons. And then the 2 electrons that had not yet been assigned were placed onto sulfur. And so this is why we would say sulfur expands its octet beyond 10 electrons. So you'll see examples like this where you end up expanding the octet of sulfur, and I think we worked on this last time, that the formal charge of sulfur would be, we take all the bonding pairs, cut them in half, keep the lone pair on sulfur. So sulfur has 6 electrons surrounding it. That's 6 - 6 for sulfur for neutral formal charge, and then the fluorines are all 7 - 7 for neutral as well. So you'll see examples like SF4 here, where you have an expanded octet on your central atom, and that's okay as long as, one, you're in the 3rd row. You won't see 2nd row. You won't see like OF4 form with a stable molecule like SF4 does. You're putting the fluorines too close. Oxygen smaller than sulfur. You're putting the fluorines too close together. The compound just can't form. In that regard, you have too many electrons that are all repelling each other in a close area. But SF6, sulfur's bigger. You can pack more than 8 electrons around sulfur, and we get to that type of a structure following our Lewis structure rules. Okay, so let's press forward into some other Lewis structure. Back to a couple well, actually I got rid of this. Let's even go back to a couple simple ones that we'd already done to see that we get to the same Lewis structures. for things like water, OF2. So if you recall, like water, we had come up with this Lewis structure by looking at the dot diagram and kind of filling in hydrogens, one lone pair. So we take another hydrogen, pair them up. So with the dot structure, we can get to a Lewis structure for OF2 pretty easily. And within our Lewis structure rules, we can as well. So I just wanted to show that you can also apply the rules that we came up with for 3 or more atoms. So taking 1 times 2 plus 6, that's 8 total valence electrons, central O, 2 hydrogens. And again, I'm going to write them linear, but again, we're not thinking 3D shape here. So the real molecule doesn't look necessarily like we sketch a Lewis structure. We'll have to think later about 3D shapes. And then that's 4 of my electrons, the 4 left over onto the central atom. So the 4 extra electrons are placed onto the O atom. So we can get to the water Lewis structure either just from a dot diagram or from the Lewis structure rules, the more formal Lewis structure rules. Now, when do you follow the rules versus when do you not? I think only when it's a really simple molecule. If it's like O2, N2, Cl2, water, ammonia, very, very simple. CH4, pretty simple. I can just follow a dot diagram construction for their Lewis structures. Whenever it's anything more complicated, something maybe I haven't seen before, then I just think I'm going to apply the rules. So OF2 would be 6 for O, 2 times 7 for the fluorines. That's 20 total valence electrons that the structure needs. So and the O is central. I think it's pretty, that's why you write it first. So O, and then the 2 F's are attached. So I have OF2. If it were like oxygen, fluorine, we probably would have called it like FOF or something different. You know, if we wanted this compound to be, you know, fluorine in the center, which would be weird. If it were fluorine in the center, I would have written the formula differently. So if you're wondering, how do I know O is the central? It's because we wrote it first. You know, so we're usually not trying to hide or be too confusing with O is the central, and then the 2 fluorines are both attached to the O. Complete the fluorine octets with lone pairs. And how many electrons is that? Well, it's 8 around each of them. That's 16 electrons. The 4 electrons left over, place onto the O. Now, for these, for this molecule here, what's the formal charge of O? Well, oxygen has 6 electrons, it's neutral. Fluorine has 7 electrons, so it's neutral as well. So these are all neutral. Same thing with water. Its atoms are all neutral in formal charge. What about the real charges? What are the real charges of H and O in water? Which atom's more electronegative, O or H? Oxygen's much more electronegative. Oxygen's the second most electronegative element, only behind fluorine. So oxygen's going to pull the bonding pair electrons in towards itself, and oxygen's going to pick up a partial negative charge, or hydrogens are going to be partial positive. So you can think, okay, from the formal charges being 0, don't mean the real charges are 0. That just means if the bonding pair electrons are equally shared, the charge in H would be 0. And then I know that they're not equally shared because oxygen's going to pull the electrons more closely towards itself and adopt a more negative charge. And then in OF2, the exact opposite happens. Fluorine's more electronegative. So fluorine's going to pull the electrons off of O, and it's going to win the tug of war. So fluorine's going to pick up the bonding pair being a little bit more shaded closer towards the fluorine atom, giving the fluorine the partial negative. And then oxygen going positive as a result. And then this coincides with differences of electronegativity. Fluorine's the most electronegative, then O, then H within these 3 examples. Now, what about our oxidation number rules? If you remember, the oxidation number of hydrogen in molecular compounds is +1. So our oxidation number, let me change colors here. So let's put the oxidation numbers in blue. So we have a +1 oxidation number for hydrogen, and then -2 for O by oxidation number rules from chapter 4. And so what you can see is that the negatively charged water ends up negative, matching the negative sign of the oxidation number from chapter 4. So the sign of the oxidation number is meant to predict the charge that that atom is going to have when we consider the real bonding and the electronegativity differences within these molecules. Oxidation number rules for OF2, -1 for the fluorines. Fluorine's always -1 in compounds, so oxygen goes +2 as a result. And you can see we have the same sign for our oxidation number and our true actual charge. Let's do a couple more examples. PF5. So our valence count, 5 for phosphorus. 7 for the fluorines, 5 of them. That's 40 total valence electrons. So how about a central phosphorus with all 5 fluorines attached? And again, I'm not thinking what this might look like. I'm just trying to get 5 fluorines sketched. And then lone pairs around each of the fluorines. And so 5 times the 8 fluorines, that's all 40 electrons. So there's 0 electrons left over for phosphorus, but that's good. Because phosphorus right now has 5 electrons closest towards it. It has a neutral formal charge, so does the fluorine that has a neutral charge. Phosphorus appears to be expanding its octet because it has 10 electrons surrounding it. If I look at phosphorus, I have 10 electrons, 2, 4, 6, 8, 10 surrounding the phosphorus atom. Now, does the real atom have to really expand its octet? Well, not really, because the whole idea of these compounds is they only form with really electronegative atoms that are going to pull electrons back away off phosphorus. So it's like the Lewis structure shows like an overloading of the electrons on phosphorus, but then the fluorines are going to say, hey, you know what, how about we remove some of those for you and shade those electrons closer towards the fluorine. So the fluorine adopts a partial negative charge on all these atoms, and then phosphorus ends up having a partial positive and a pretty big partial positive. If you do whatever the negative charge was on each F, phosphorus's charge is 5 times that. So we end up with a pretty big positive charge on phosphorus. And that's kind of like making room for those extra electrons by allowing fluorine or having fluorine as an atom that can pull those electrons away. So a molecule like PF5, this doesn't form with like hydrogens. We don't get like PH5 forming because hydrogen can't do this. And we then pack too many electrons around phosphorus, they repel each other, the compound doesn't exist as a result. But a compound like PF5, this is a stable enough compound to exist. I can't remember if I do this later, but SF6 is another common example. Just like PF5, it's just a central sulfur, and then you can have 6 fluorines surrounding sulfur, and it's a stable enough compound you can actually put into a gas cylinder and ship it around the country, and you can even breathe it in. I don't like doing this demo, but there's a demo that some people have done, I've done it a couple times, where you breathe SF6 in and your voice becomes very deep instead of very high pitched, so it's the opposite of helium. Instead of making your voice high pitched, like helium makes it very low pitched, and then you can feel the fumes. It's probably not healthy to do, so I don't particularly like doing that demo anymore. But these are molecules that exist is the point. So we're not sketching structures of hypothetical molecules. This is something real, a compound that exists that's stable enough to put into a bottle, ship around the country, etc. So what about ClF3? Well, 7 for chlorine, 7 for the fluorines, so that's 28 total valence electrons. So central chlorine, the fluorines around, and so then lone pairs on the fluorines, that's going to be 8 each for the fluorines. And I don't think there's too many shortcuts on Lewis structures. Sometimes you sit here and think, okay, should I just memorize all these? Don't memorize all the Lewis structures. These rules are pretty easy. Just to count up to get to the 28 to see we've assigned 24. And these 4, they go onto the chlorine. So we put an electron pair here, an electron pair there. And the only way I know to put those 2 electron pairs on chlorine is either, I guess, to memorize this structure or just to understand the rules. And I end up with 4 leftover electrons in my count. So I put those on as lone pairs around chlorine. And so I usually just stagger them because I don't want to put 4 in a row. So I'm just staggering 2 electron pairs on chlorine. We'll look later at what the actual shape of this molecule looks like and how it can somehow put all these electron pairs around it. But that gives us 28 total electrons. And then if we think about the formal charge, what's the formal charge of chlorine? Well, chlorine looks like it has the 3 pairs of electrons from the bonds and then the 2 pairs of electrons. So that's 1, 2, 3, 4, 5, 6, 7. Another way is if I break these bonds in half. So take the bonds and just put 1 electron closest to each atom. And then let's box the structure like this. So we're keeping the lone pairs all in the central chlorine because they're attached to that chlorine. And then we're taking half of the bonding pair electrons. So do you see how that's 7 valence electrons around chlorine? So that's neutral. So let's say neutral chlorine, and the fluorines are all neutral as well. We've seen that Lewis structure a bunch of times, 7 minus 7 for the fluorines. Those are all neutral. So if you're noticing a theme, we have some expanded octets in the case, or a lot of Lewis structures that tend to exist with neutral formal charges all the way around. Doesn't mean the formal charges always have to be neutral, but it's a common feature of compounds that they tend to have neutral formal charges that are close to zero, if not zero. Why is that? Well, a given nucleus only has so much pull. A nucleus, if you will, has enough positive charge to pull in roughly its valence count of electrons. And if we're going to go negative, we have to then have another thing attached to it that allows us to get the plus minus. So getting a negative versus positive formal charge in a compound takes like some give and take between the atoms. But in the case here, we end up with zero formal charges all the way around for ClF3. Now let's think about the actual charges for a minute. Fluorine's, of course, more electronegative, pulls electrons away from the chlorine, and the fluorines are all partial negative. Chlorine, as a result, is partial positive. So fluorines are definitely negative here on this molecule, not truly zero. Just zero if the bonding pair is equally shared, but the bonding pair won't be equally shared because fluorine's more electronegative. So we let electronegativity kick in, get the fluorines are all negative. And then if we go back to oxidation number rules, we would have said by oxidation number rules, the fluorines are all -1, and then the chlorine should have been +3. So we're getting the sign, chlorine should be positive from the +3 oxidation number, fluorine should be negative from the -1 oxidation number. And the same thing with phosphorus. These would all be -1s for the fluorines, making the phosphorus by oxidation number rules +5. Now, is phosphorus truly +5? No, it's not nearly +5. Fluorines aren't really -1, but the fluorines end up negative, the phosphorus ends up positive is the prediction we get from oxidation number rules. Let's look at some cations. So like a cation isn't any harder than an anion. We just have to know to take electrons away. So when I'm counting up for NH4+, I just start with a normal count for nitrogen of 5. The normal count for hydrogen, 1 times the 4 hydrogens, and then I have to subtract an electron for that positive charge. So if I showed NH4 with 9 electrons, that would have a neutral charge. If I showed NH4 with 10 electrons, that would be NH4 minus. If I showed NH4 with a positive charge, then that would be 8 total electrons within the Lewis structure. So 5 plus 4 minus 1 is 8 total valence electrons. And again, let's make sure you see, sometimes when we deal with hydrogen, we get a little confused on if we're counting all the electrons. We're just counting the valence shell electrons because those are the ones that are in the outermost areas of the atoms. They're the ones that interact with each other to make bonds. And so we're counting up our valence count. So we have a central nitrogen, 4 hydrogens. So that part's pretty easy because hydrogens don't need any more electrons. Hydrogens are happy with 1 bond. And then nitrogen here only has 4 bonds within this Lewis structure so far. What are the relative charges here? The formal charge of hydrogen should have 1, has 1. So the hydrogens are all 0, formal charge. And then the nitrogen is positive. Why is it positive? Nitrogen should have 5 electrons, only has 4. So we're thinking if nitrogen had 5 valence electrons, its charge would be neutral, only has 4. Therefore, it's where the positive charge lies in the formal charge writing of the charges of this molecule. Now, what is the true charge of nitrogen? This gets a little confusing, and sometimes we won't always ask. In fact, most structures and most questions on the test aren't going to be like, sketch a Lewis structure. What are the actual charges? Because this gets a little bit tricky, and I don't want it to be too distracting, but the nitrogen is more electronegative. It's going to try to shade those NH bonds closer towards itself. So it's really going to reduce the charge of nitrogen from +1 down to a lower charge, but probably still positive. Hydrogens will pick up some of the positive charge. So that charge can distribute across the hydrogens just by thinking how these dipoles are all going to point in towards the nitrogen because it's the more electronegative atom. So nitrogen is the 3rd most electronegative atom. Chlorine is in a tie. So like chlorine, nitrogen, oxygen, fluorine. Those are the 4 most electronegative atoms on the periodic table. Let's look at NO3, then let's look at ozone after that. So NO3 minus, this is, and let's just take a look at our count first. So 5 for nitrogen, 6 for the oxygens times 3, add 1 for the negative charge. So just remember, negative charge, we're adding electrons. Positive charge, we're removing electrons from the Lewis structure. So that gives me a total of 24 valence electrons. So I start with my central nitrogen, and then 3 oxygens, give the oxygens their lone pairs. And then again, don't put a lone pair on nitrogen just to fill its octet, because the rule is give the non-central atoms an octet with lone pairs, then count your electrons that are thus far distributed. So that's 24 electrons distributed. So it leaves me no electrons behind to put onto nitrogen. And if you recall, we had a similar looking Lewis structure before for like BF3 on Monday. So BF3, if we contrast, BF3 also has 24 electrons. If you remember, for BF3, we got to this Lewis structure here that looked very similar. In the case for BF3 is that this was good because my formal charges were all 0 for BF3. Because boron only has 3 valence electrons, it has 3, it's happy. Fluorines are neutral, they're happy. In fact, fluorine's trying to pull electrons away and make those fluorines partial negative because fluorine's more electronegative. So this would be our best Lewis structure, or our dominant Lewis structure for BF3. Well, nitrogen's a little bit different. Nitrogen has a different charge. It has a higher charge, has more protons in its nucleus. Now what that changes is the formal charge of nitrogen. So the formal charge of nitrogen should have 5 valence electrons for a neutral charge, only has 3. So we have a +2 formal charge here. And so this is just like H2CO formaldehyde, where we have an atom that's deficient of an octet that has a charge. We should be able to pull an electron pair in and make a double bond. Which oxygen should I choose? Well, we're going to talk about that in a minute, but we could choose either of the oxygens to make one double bond, but we're going to have to stop at one double bond. When I make one double bond, that reduces and changes the formal charge down to be 5 - 4 now for nitrogen. So it changes nitrogen's formal charge to be +1 instead of +2. So that reduces the formal charge. That's good. That's why we make double bonds, is to reduce magnitudes of formal charge. This O here is now 0, where the other 2s are -1s. These oxygens should have 6, they have 7, so that's how we get -1. So the formal charge, we've done this a bunch of times. If you're ever getting confused, you're just taking the formal charge calculation is to take the valence electron count and then subtract the half of the bonding electrons and then subtract all of the non-bonding electrons on an atom. And what we mean by half of the bonding pairs, that's breaking the bonds in half. So if you're looking at like the oxygen, it's like we have 2 bonding electrons, we'll take half of that, that's 1. And then all the non-bonding electrons, that's 6. So that's where we'd come up with this being like 6 minus the 1 from the half of the bonding pair, and then minus the 6 non-bonding to go to -1. I like to draw boxes because it's not an equation. I forget equations. I can easily draw a box and I can remember how to draw a box. I'm just boxing the electrons that are owned by the formal charge rule by breaking covalent bonds in half and just sketching out what the electron count looks like and then thinking of what the charge of the atom would be as a result. Okay, so I have -1 O's on the 2 O's and then a +1 for nitrogen. Do I do it again? So that's the question for nitrate would be, well, why don't we do this then? Why don't we go double here, and then just leave the 1 single? So if I do this, this seems to be a good idea because I've now reduced the formal charge of nitrogen down to 0. And then these are now 0, and then only the 1 is -1. Is this an even better Lewis structure than the one with 1 double bond? It's a bad Lewis structure because we've expanded the octet of nitrogen. Nitrogen's too small. Nitrogen, the smaller the atom, the harder the atom would have having all those electrons in a small location because electrons repel. So second row atoms cannot expand their octet. So when we look at a central atom, we see 10 electrons around the atom, that just can't be. 8 would be the maximum for a second row atom. Those expanded octets are only coming up in third row or greater. So like sulfur, chlorine, phosphorus, those atoms can expand their octets within some of their Lewis structures, but not nitrogen. So nitrogen's best Lewis structure would stop here within this Lewis structure with 2 singles and 1 double bond. Now there's a very important topic called resonance we're going to get into in a moment. I'm going to save that for a slide after we look at the Lewis structure of ozone. Because resonance is going to be an important trend or way of thinking of, well, what happens to the real structure when there's multiple Lewis structures we could have sketched that all look very much the same, or what we call equivalent Lewis structures. But let's look at ozone, then come back to the question of resonance. So for O3, at first O3 seems tricky. It's like, well, which one's the central atom? Is it the O, or the O? Well, of course it's the O. So like an oxygen has to be the central atom. In fact, O3, unless it's something weird where it's like a triangle, which it's not. So there's no weird structures here where we're going to have like 3 atoms connected, or multiple atoms in a ring structure. So we have 3 O atoms connected together, and then the one in the center is the central atom. And so if we're following our Lewis structure rules, we would start with a Lewis structure like this, where we have lone pairs in the non-central atom. We can count up our valence count, 3 times 6, that's 18 total electrons. And so we've distributed 16 over here so far, so that leaves 2 electrons behind. So 2 electrons left over onto the central oxygen. And so oxygen's still deficient of an octet. We can't add another pair of electrons because that would be too many. That would be 20 electrons. We only have 18 to distribute within the Lewis structure. And so the formal charge here is now +2. We should have 6 electrons. We only have 4, so this is what I mean by sketching this box here. For the formal charge, so a +2 formal charge, we should be able to make a double bond. So we make a double bond here, and then that reduces this formal charge now down to be +1, 6 minus 5. And then one of the O's is 0, and the other O is -1, formal charge. And so that's one of our actually 2 best Lewis structures for ozone. The other one being just putting the double bond on the other O and keeping the single on the other side. So for ozone, we can do this for nitrate, but you can sketch you could say, well, there's a second Lewis structure. That would just be, we'll put the double bond over here, and that this is actually a different Lewis structure. Looks the same. Looks like I just rotated the molecule, but it's just saying I can make the double bond with the one O or the other O. And I can make the double bond in either spot. Now this leads to an important issue. And it comes back to an idea that I mentioned at least once or twice before, and that Lewis structures aren't real. Lewis structures are just things we wrote on paper. We're trying to represent something real. We're trying to get a picture of something that's truly exists and what it might look like. And for a lot of molecules, a lot of ions, there turns out to be one really good Lewis structure, and that turns out to be one really good picture for what something looks like. Like almost everything so far we've looked at, like NH4+, like water, OF2, all those examples, is like we have one good Lewis structure, so that's a really good representation of what the one molecule might look like. In the case of having multiple Lewis structures that we can sketch that appear to be equivalent, something complicated happens within molecules. Let's take a look at a slide like this. So if we actually look at the structure of ozone, what we see is that ozone looks identical in terms of the 2 O atoms. It's not like one of them looks neutral and the other one looks negative. They both look identical. So both the bonds appear to have the same length. So the bonds in ozone truly have the same length as each other. One's not shorter, because double bonds are usually shorter. Remember, single are usually longer. So if you take a snapshot of ozone, you don't see that. You don't see one shorter, one longer at any given moment in time. It turns out their bonds are always the same length between the 2 O's. Well, how does that happen? It happens through something called resonance. And resonance occurs, and it's also a consequence of ozone doesn't care that we just sketch 2 different Lewis structures. So ozone's like, okay, I get that you just sketched, say, Lewis structure A and Lewis structure B, and you might be thinking, okay, some of the times ozone looks like A, some of the time like B. Real ozone says, well, why don't we just blend the 2 together at all times? So what happens with resonance is the molecule exists as the average or the composite of those 2 structures. So the true structure is the composite or the average of those 2 Lewis structures, and the average would look like this. It's hard to know what to do with the lone pairs. I'm going to leave the lone pairs out of this discussion, but I'm just saying you're going to average out a single with a double. So the average would be that each of these bonds here would look like having about a 3/2 bond. What does that mean? Well, a double bond, well, we talk about this a little bit more in chapter 9, but bond order is just the number of bonds that are being exchanged, like number of bonding pairs. So the bond order would be equal to 2 for a double bond. The bond order for a single bond would be equal to 1. So a single bond is sharing 1 pair of electrons, a double bond is sharing 2 pairs of electrons. Ozone, what its bonds look like are bonds that are sharing a bond and a half. They're sharing 3 halves bonding pairs. So it's like I'm taking the 3 total bonding pairs of electrons and spreading them across the 2 OO bonds. So I have two bonds between O on either side. I'm just sharing those 3 bonding pairs of electrons at all times. So instead of one of them being double, one being single, at all times, it's like they're the average of that. So at all times, it's the average, which is about a 3 halves or a 1.5 bond. If we'll at some point compare some bond length trends. It's one of the slides, I don't think we're going to get there today. But if you look at bond length trends, this is kind of right in the middle of the single bond for 2 O's and the double bond for 2 O's. So a double bond distance would be shorter, single bond would be larger, and this is kind of right smack in between the 2 bond lengths for those bonds. And this is anytime we can sketch equivalent yet different Lewis structures. So this is going to come up a lot. It just actually came up with nitrate. We'll see in the next slide of how nitrate does this too, that anytime we can sketch Lewis structures where there's more than one Lewis structure that looks equivalent, then the real molecule averages out those Lewis structures. Let's take a look at nitrate. Because nitrate here, we actually get an interesting bonding model if we look ahead to something from chapter 9. So for nitrate, what we have is the same case where I could make the double bond here, or I can make the double bond with this O, and what's going on is that we're moving this electron pair in here, and this electron pair is moving out here. So that's like a resonating effect of those electrons moving very quickly and not even doing so as an averaging effect, but this taking place across the whole structure at all times. And so then if we kick this electron pair in here, we can move this electron pair back to make the double bond over to here. That the real structure of nitrate, what it should look like is the average. The average would look like this. We just do the little dash arrow to indicate it's not single, not quite double. In fact, what bond order might you call these bonds here? Well, I'm taking 1, 2, 3, 4 bonding pairs of electrons and spreading them across the 3 NO bonds. So it's a bond order of about 4/3. Now, we don't ask too often about the charge of the O's, but you can think the oxygen charges are also kind of balancing out. The formal charges are just going between -0 and minus. So the charge on the O atoms in the composite structure are about -2/3. So the charge is balancing out too. I could have showed this on the ozone slide and maybe should have, because that's why the O charge, if you look at the charge distribution picture on the previous slide, the 2 O's on the outside appear to have the same charge because they're balancing between -1 and 0, averaging out to about -0.5. But the key being that they're the same charge on the outer O's. These O's on the outside of nitrate all have the same charge as each other. Now the bonding model picture is very interesting. The idea, we'll see this more in next chapter, is that when we make a double bond, we use these like pi, the p orbitals make a pi bond in nitrate. And if you picture making all those bonds at the same time, you get like one orbital that shares that extra bonding pair. So it's like each of the nitrate bonds is like a single bond, and then plus that extra bond that's an all-time bond, that bond shares that electron pair across the structure at all times. So the key for nitrate, and this is really the question we tend to ask, do you think nitrate has one bond that's shorter than the other 2 at any given moment? The answer is no. Nitrate at all times has 3 equal length NO bonds. So the real molecule of nitrate looks like the average composite structure. It never looks like Lewis structure A or Lewis structure B or Lewis structure C. This is also not an equilibrium. It's not like A is moving to B, moving to C, and then going back and forth really fast. The electron pair just distributes across those 3 bonds at all times. It's a very important concept. You'll see this a ton in OChem. OChem talks a lot about resonance when you get there. So you'll see some questions on our exams. It's like, are one of the bonds different length than the other? No, all 3 bonds in nitrate have the exact same length at all times as a result of resonance. I guess I did get to the slide here today. So this was looking at the length of like an OO bonds, 1.48 angstrom, OO double bond, 1.21. maybe ozone's not perfectly in the middle, but it's in the middle. It's in between being longer than a double, shorter than a single bond in terms of its length. And you can see here that the single bond's always longer than the double. And so as you're packing more electrons between two atoms, you're decreasing the bond length. And then you can think we're going to increase the strength. So if you go from single to double to triple in terms of bond length, that for a given bond, the single bond is always longer, the double bond is always longer than the triple. The triple is the shortest bond. And then we can also then say, well, what about the bond strength? The energy it takes to break the bond, single bonds end up being the weaker bond. So single bonds are weaker because they only have 2 electrons serving as their glue. Double bonds are stronger, triple bonds even stronger. There was a slide, I don't think I have it queued up here in order, but a single bond is about 400, I think it's 348 if I remember the exact number for carbon-carbon double. So I think if you look at the strength, this was about 348 kJs per mole. The carbon-carbon double, I always remember because it's the area code of Columbus, it's 614 kJs per mole. And then the carbon-carbon triple, this is around 1,000. I don't have that one memorized, but it's in the range of about 1,000 kJs per mole. So you're seeing the triple bond stronger, takes more energy to separate a triple bond than a double bond versus a single bond. So electron pairs shortening bonds, but then strengthening them as we're adding to the glue that links those atoms together. Okay, so in general, mostly I finished chapter 8, so we have some review questions. Let's look at one here, and then we'll take our quiz and be done for the day. So let's look at sulfate. Which statement is true for sulfate here? Should all of its bonds have the same length or 2 shorter than the other? Well, what this question is going to need us to do is to look at its Lewis structure. So let's consider the Lewis structure of the sulfate ion. Sulfate essential sulfur. Let me count up real quick. 6, 4 times 6. Plus 2 for that charge. That gives me 32 total electrons. And so we'll have a Lewis structure that looks like this. And so that's all my 32 electrons, so no lone pair for sulfur. And then this Lewis structure is pretty good. We're satisfying the octet role of sulfur. We're satisfying the octet role of all the O's. All the oxygens happen to be negative formal charge. They're all 6 minus 6. Or I'm sorry, 6 minus 7. We have 7 electrons around each of the O's. So 7 electrons per O gives us that negative 1 formal charge. Sulfur is a plus 2, should have 6 and only has 4. Has these 1, 2, 3, 4 electrons closest to it. And so should we reduce magnitudes of formal charge though? So we have this Lewis structure. I'd say this is a good Lewis structure that follows the octet role. We also then could write a Lewis structure where we make 2 double bonds. Why might I make 2 double bonds and leave the other 2 single? Well, if I do that, then my sulfur becomes 0. So 6 minus 6. If I make 4 double bonds, then sulfur goes negative. So I don't want to make 4 double bonds. I at most want to make 2. So my sulfur goes 0. These 2 oxygens go 0 formal charge. These 2 stay negative. Now, which Lewis structure is probably better? Probably this one. But do you see, even if you think this is a good Lewis structure over here, that somehow we have to have resonance kick in. That somehow we have to have resonance kick in to say, well, I could have wrote the double bonds over to here, and then they would average out. So the real structure for sulfate, if I'm thinking that this is the better Lewis structure, that it has to somehow still resonate. And those bonds would have the same length as each other. And if I'm looking at the Lewis structure that I think is best, that all those bonds look identical, they're all single bonds. They all have the same length. So all the bonds have the same length in sulfate. It doesn't matter which of the Lewis structures you look at. You either have to consider resonance for the one that has the double bonds, or you just see it more clearly with the ones with single bonds. Okay, let's take our quiz today. Keyword for today is Avogadro. But that'll do us for today, and I will see you guys back here on Friday.